Now let's talk about and have a look at the setup for this reaction, the SN2 synthesis of 1-bromobutane. In this synthesis, we are going to employ a new technique called refluxing. What is refluxing? If you know anything about a condition called acid reflux disease, where the acid rises up the esophagus and then comes down again to enter into the stomach, is a condition that many suffer from. Biologically, that's not something we want to suffer. However, in an organic lab, we are going to actually utilize that technique to accomplish certain reaction synthesis that otherwise would not happen very easily. In the case of organic refluxing, what we have is a pot or a reaction flask in which we boil our solvent up to the boiling temperature of that solvent. And the solvent has all our reaction components dissolved in it. Then it's attached to a condenser here, which is also connected to water inlet as well as water outlet hoses. Water flows through this black hose inside the condenser on the bottom, and it exits from the top back out into the drain through this yellow hose. Now, as I had told you previously, in a condenser, the water must always flow against gravity. Hence, this time, the bottom hose is where there is water inlet, and it flows against gravity going up and then comes out through the top hose. Our solvent will boil in here, and our reaction solutes, which are going to be hydrobromic acid and butanol mainly, they are going to react with each other in an SN2 reaction, and then over time our hydrobromic acid and butanol will go down in concentration, while the concentration of bromobutane will rise. In your lab notebook, I expect to see the physical constants such as the densities, the boiling points, the melting points, and other data concerning the hazards of all the solvent as well as the solutes that we are using in this reaction, especially bromobutane and butanol. The boiling point of butanol is much higher than the boiling point of bromobutane. Bromobutane is practically an alkane with a substituted halogen in it. Hence, we expect it to have a low boiling point. While butanol, being an alcohol, participates in hydrogen bonding. As a result, we expect the boiling point of butanol to be much higher. So, as we are boiling our solvent and our bromobutane is converted to our butanol is converted to bromobutane, over time, the boiling temperature of our mixture should go down. If we were to stick a thermometer inside and see the temperature, we should see that the temperature drops as we lose butanol to the synthesis of bromobutane. So, through our refluxing, we will lower our heating rate, adjust it on the controller for the heating mantle here. That's connected to the electrical outlet. Now, as the reaction boils, the vapors from our solvent will rise up, and we want to control the heating in such a way that the condenser, the line on the condenser is somewhere in the middle but not too high. That's optimal for the reaction. Regardless, we have connected one more glassware here, the vacuum adapter, because we are going to make sure that any hydrobromic acid fumes that are generated in this reaction do not just escape through the condenser into the hood, where it can damage the hood, and we will lower the hood later on before we start the reaction, so that all the vapors are actually removed from this room rather than ending up in our lungs. But at the same time, by attaching this vacuum adapter, which is connected with a hose to this trap. Now in this trap, what we will have here is a solution of sodium hydroxide.